Thank you very much for the organizing committee to invite me here. And I have been visiting Punji University for many times, but this is the first time I come to these brand new locations, which look very wonderful and marvelous. And today I'd like to share about the so-called AI-empowered robotic perceptions and navigations. Now, we have witnessed the explosive era of AI, and we have seen many applications. And on the other hand, robotics also we have seen, and also we expect there will be a lot of the application in the engineering in societies. And AI, of course, now have been applied to many areas of engineering, science, society, and so on. And one of the area of application is the robotic. And people in the robotic nowadays are trying to use the AI technology to enhance the capability of robot. Now, especially we know robots here are dealing with various environments and which are difficult to model. And use AI technology will enhance its perception and its manipulation technique. Now, I would like to focus on the perception and navigation. And we know perception is an essential capability of robot. Just like a human being, we need to be able to see our environment, to understand our environment in order to carry out our job, carry out our tasks, and so on. And of course, robot also deploy or use the sensor technology like LiDAR cameras and to sense the environment, but you need to have a technique algorithm AI here to understand the environments, and so that the robot have the capability to navigate in the environment. So navigation is definitely a very important technique for robotics. And since my topic here is on AI in application of robotics, I would like to use a few cases or few studies we have to illustrate how AI can be used to improve or enhance robots' capability in perception and navigation. So this is my content here. I will just briefly talk about a few examples, a few studies we have carried out to enhance the perception capability of robot, and then I will talk about how the embodied AI can be used for the object navigation for robot. Now, we know that for perception here, we have two methods. Traditionally, we use a hierarchical so-called modular approach here, where you use sensor here to collect the data of the environment, and then you use algorithm here to extract the features, and then try to match the features to detect the motion or estimate the motion of the robot and build the environment and estimate locations so that you can carry out your job of navigation and so on. So this kind of modular approach, which is more mature and interpretable, meaning that we understand each of the steps here, what we're doing, and what accuracy we can achieve, and so on in a particular environment. And of course, nowadays more and more research towards so-called the end-to-end network here. That means that we just collect the data by the sensor here, and then train our network here, and network will just output of the actions which need to be carried out. Perception is quite challenging because of the environment dynamic here. For example, when robots operate in the outdoor environment here, you have the issue of lighting change, right? And also you have the adverse weather, sometimes heavy rainings here, foggy environments, and some environment here may not have any feature available, so-called we call sparse feature, and some environment which is a reflective survey. For example, in the building, you have glass window and so on. So there are all kind of environment which definitely will affect the performance of the sensors here. And in developing the robotic system, you have to consider all those different factors. And the other, of course, is is the cost factors here, because we engineer here in industry here, every sense counts. So what kind of sensor you need to use, it depends on your requirement. It's on the accuracy or what, you know. And so in this case here, you adopt sensor which is may have a limited accuracy, range, and also field of views and so on, right? And you can see all kinds of the environment. Environment may change. So in this case here, you need to deploy multiple sensors here using the multi-modality sensor fusion technology here, so that even though the environment is changing and your system here still be able to adapt to the environment. Let me just use 3 case studies we carry out. And first is the bio-inspired UAV perceptions. And we know sensor here has a limited or fixed view of view. And in nature here, like all here, when you want to see the environment, he fix the body, but then he can turn around. Just like our human being here, we want to see our environment here. We need to turn around to see, but we not just to turn around, but we want to see area which we are interested in, right? So, but how the robotic know which area, is interested in, which area has more feature can help it to localize itself, or to perceive or to understand the environment better, and so on. So this is the challenge. So by so-called by using for example, inspired by the hour here, and for example, this UAV here, we use the LiDAR to detect the environment, but LiDAR we know have a fixed or limited field of view, but we can actually modelize it to install a motor here, so that you can do the rotate the LiDAR to better view the environment. But as I say here, the question is, how can you be able to, according to the environment here, to know where you should focus on, so that you can have a better understanding, or have a better features to help you to localize itself. So in our study here, we actually use one of the control technology we call model predictive control. But the important thing here is, how do you what kind of the cause functions? I mean, what kind of focus you should emphasize. And so in our technique here, we especially use AI technology here to design the cause function, so that you can balance exploration and exploitations. In the sense that you have 2 causes. One is that when you scan the environment here, when LiDAR do the rotating, you have extract the feature, and certain direction have a better feature to help you to do, or to better localize itself. And then in this case, of course, that what angle you should rotate it to, and so that you can improve your localization accuracy. But on the other hand here, you also want to explore new area, right? So in this case, how do we know, where and how to explore a new area? And we use network or CNN, convolution neural network here, to leverage on the image you taken in the environment here, and so that how to take a certain angle, so that you can have a new feature to help you to localize. So essentially is design of the cause function, so that you can balance the exploration and exploitations, so that you can have a better perception of the environment. So this, we say when you use learning technology, mainly is the neural net here to actually to interpret the environment, to help you to say, okay, which sector or which area can help you improve. But of course, this will require a lot of the data here to train the system here. So we actually collect data from many different environments, for example, in the outdoor environment, in the cave, or in the underground, and also in the forest, and so on, right? So that in this case, this data will help you to train a better system to be able to adapt to different environment, to better sense the better focus on certain area. And we do some comparison here. When you just fix the rotation speed of the data of the motor, or you just design your model preview control based on the the feature you have explored, and then to design your course. And in this, but what our approach here to check between exploration and exposition here, you can see you can have a much better performance. You can adapt to the environment better and to achieve better accuracy in your mapping and localization. And we demonstrate this in different platforms like UAV doing the very mapping in a complex environment, or use the robot dog here to map the terrain area and so on. And you really can see that with the AI or with the learning technology here, you can better focus on certain area of interest and better map your environment, better achieve a better accuracy and so on. So this is the UAV mapping, and then we also have the robot dog here in the terrain area here, outdoor, indoor, to map your environment. Okay, so because of time limitation here, I don't want no detail. And another dynamic environment is the lighting change. As I say, when you go outdoor here, or even in the indoor environment here, when you have a glass window, the lighting is always changed. So if you use the camera to perceive the environment here under the lighting change here, then in this case, the traditional method of the feature extraction will always face a lot of challenges here. So we use the deep learning technology here to better extract the feature when lighting is changing from, for example, from dark to bright, or from bright environment to a dark environment and so on. Of course, so in this case here, the question, of course, how do you design the network here to better change? The other thing you need to take into consideration is in the edge side here, you don't have a sufficient computing capability here to deploy or to process all the camera data and so on. So in this case here, how do you lighten the computation here so that you can deploy your algorithm here in the edge side here, so that it can be deployed in the actual robot here. So in this, we actually combine the front end and the back end, so that you can enable this robot here, or the algorithm here, learning-based approach here can be deployed in the environment, in the actual robot. And this is just some demonstration here. In the environment, we're trying to extract point feature, light feature, and plane feature, but then the lighting is changing drastically. And in this case, with the learning-based technology here, you are still able to very robustly to extract the feature here, so that you can still able to localize the cell and so on. And the other application here, in many industry environment, it is not possible for you to collect the data to build a map in the daytime because of the operation of the factory. But when you're going to collect data in the nighttime here, whether the map you have built can be used in the daytime or not. So, but with our technology here, whether you collect data in the daytime or in the nighttime, and the algorithm, the system here is able to adapt this the changing environment and to help you to navigate when the lighting is changing and so on. Another application of AI in our navigation here, we call it embodied texture cue for loop closure or localization. We know robot will have difficult to localize itself, especially in the so-called degenerate environment, for example, in the long corridor or in the cave, underground environment and so on, right? So for human beings, when we do the navigation here, we may not going to, precisely localize ourselves, but then we rather to see the environment. For example, we are going to certain unit of the building here. We look for the number of the building here, and we look for the number of the the unit number and so on, right? So in this case, we actually can combine the LiDAR-based navigation together with so-called OCR, which can capture the text informations so that you can better localize itself. And now also, for example, in the environment here, you have many exit, entrance, and so on. This, name, and so you can build up this so-called the text graph here and text graph here, so that some text here may be unique. For example, this office number, but some text here may not be unique. For example, exit and so on. And so in this case, you can use different property of the text here to help you to navigate, to localize yourself. Right? So especially in the case when you don't have a pre-built map for the navigations and so on. These are the application of AI for perception and localization using the traditional method here, which you build a map here and you navigate your robot from point to point. But in a lot of application here, you may not have a pre-built map here, and you don't have a specific the location or point of where the robot should go. For example, you ask robot here to do something, to fetch something for you, and we don't know where is the location of this robot and so on. So in this case, we can now talking about so-called embodied AI-based navigations. And so embodied AI, basically we know that you have a so-called vision language model, which is combine the larger language model together with visions, so that you can build up the relationship between what you see and what is the text or what is the meaning and so on, right? So for example, when you ask for, you give a command to fetch a glass here, and you need to translate the text here into a certain the image, what is the glass look like and so on, right? So embodied AI, essentially, we know AI technologies have been used widely to process data, process information, right? But a lot of data you have collected here is offline. But for robot here, we really want that you use onboard sensor here to collect the data, and then use the AI here to understand the environment, and then robot can carry out certain tasks. So really, this is the integration of AI together with the physical platform here. So as I say, vision language model is quite often to use to link, to understand the environment or translate the text to or command to the image. And on the other hand here, we also use so-called world foundation model here. And because we need to predict the state of, what is the future, if you give a certain action here, what is the state of the robot here, and also imagine what is the potential outcome of the robot and so on, right? So in this case, you can combine vision language model with world foundation model here, so that robot can carry out certain tasks in the real environment. One of our projects we have been working on is on the object-based navigation using the language model. So essentially, human give a certain command here, ask robot to do something, to fetch something here, but robot need to navigate to go into search and to find the object here and fetch it and carry back for you and so on, right? So this is different from traditional navigation. For example, this is the food delivery robot here, where we build the environment and we use the pre-built environment to navigate. Although there are many challenges in this different kind of environment, but you have a pre-built map. But for this embodied AI-based navigation here, you use language model to interpret your command, and then use the larger vision language model here to know what is the environment, understand the environment, and so on. There are a lot of challenge and gap in the current study here. For example, a lot of search here, still based on the so-called greedy search, and that is not efficient enough. And then study here based on 2D representation here, which will encounter difficulty when you have the occlusion. And then also, if you use the exploration method here, that you have a very rigid the path, which is not adaptable. And because when you want to find something here, you really need to see what the best way to, to find the object in the shortest time. So in this case, you need to plan your path so that you can better, you have a better chance to see, or find the object and so on, right? So in this, really, you need to have a trade-off between exploration and exploitation. So in our approach here, actually, we build up the 3 different maps. One is use the 2D grid map here for you to do navigation, and then 2D semantic map here to understand, the environment, so that you can use language model to score the location where you have a better chance of finding the object here, right? So in this case, and also, use a 3D map here to know the depth, so that you can know the physical relationship in the environment, and also to avoid collision and so on, right? And for navigation, traditionally people use travel salesman method here, trying to minimize the distance of travel. But here, our target here is to find object here in the shortest time, right? So in this case, we actually use the vision language model to score a potential viewpoint here, and so that we need to navigate to the particular point, or the point where you have a higher chance of viewing the object or finding the object here with the shortest time, So in this case, we actually formulate a problem into travel repairment problem, so that you can minimize waiting time of each of the observation point. And I think, yeah, so here basically a demonstration where you build a different map, 3D, 2D, 3D, and semantic map here. And here is, how you use a vision language model to score the observation point, and then to find or to match the object, whether this is something you are interested in or you are finding, right? And so, of course, you can use a clip here, which is a little bit light, can be deployed, but then the reasoning capability of clip here is not that powerful. So in this case here, you may want to use the larger language model, Q1 2.5 and so on. But in that will require you have a better computing power and so on.
Embodied agent that is capable of understanding its environment and performing reasoning to locate specific objects across different but related environments. When the robot enters a new scene, it begins to explore and understand the space. After completing this exploration and building a semantic understanding of the environment, the robot stops. During this initial exploration, the robot may not encounter specific objects to find, but the robot can learn correlation, which will tie back in with a semantic understanding of the environment.
Echo, please find an apple for me.
When the robot receives a voice command such as, "Please find an apple for me," it reasons about the most probable location where such an item could be found, plans a path to that area, and begins a search. Once the object is located, the robot announces the result.
Echo, please find a bottle of cola.
Black bottle of cola.
So yeah, I think my time is done. So I just so there are still a lot of challenge. For example, here when we do a lot of testing here, your viewing angles and also the lighting will affect your result. You know whether robot can find the right object you want to find or not. The other is a dynamical environment, and of course we have also when you find something here, you need to fetch it. So in the clutter and dynamic environment here, how the robot need to judge where from which location here he can reach the object and how to grasp you know the object and so on. And the other thing here is because you need in each side here you have a limited computing power, so you can just only deploy very light model, and in this case they have a limited reasoning capability. And if you give a very incorrect or ambiguous command here, you know, if for example you ask, you know, there is a fire, but over there, but nobody need to understand what do you really want, right? If you ask to find an apple here, that's a very direct command. But then if indirect here, nobody need to interpret and reasoning what really you want and so on, right? So this language grounding and ambiguity in your command is also is quite important. The other thing here, of course, is as I say, is if you use the computational capability or power you have, right? You use the larger language model like Q1, of course, you have a better reasoning capability, but then in this case, the edge side here does not allow that. But if you use the cloud here, then there's issue like security and so on, right? So all these things here, you will need to trade off. So yeah, So as I say, you know, AI here is very important impacting vectors here for robotic development here. Especially, we can really use the AI technology here to enhance robot intelligence and the capability to carry out various jobs for human beings. So with that, I will end my talk here. Thank you.